Hey pre-calc students, Mrs. Fellon here. I am going over Unit 7, Lesson 1. So in this unit, we are going to talk about all different kinds of functions. And so we're going to explore probably some stuff you learned way back in like Algebra 1. So some of the stuff might look a little bit familiar from then. But we're also going to add in some of our familiar functions from earlier this year as well as from last year from Algebra 2. All right, so first what I want to talk about is just the format of how we can represent a function. So this first one is, and I called it f of x. This is a format of just obviously using a table. So what I want you to remember is that all of the x values here represent input values, and then f of x, this would be your output. So all of these are going to be your inputs, and these are going to be your output. So you can think of it as like x and y, but it's probably easier to think of it as more like if you input a 0, your output is 4, that kind of thing. You might have been introduced to a mapping back in Algebra 2 or Algebra 1. So a mapping is just kind of another way to write kind of like a table, but obviously a little different. And how you read a mapping, so we're going to call this function g of x, is these are really just ordered pairs. So like, for example, these are all of our inputs, these are our x values, and these are all of our outputs, which are our y values. So what this means is when I input 3, my output is -1. When I input 0, my output is 0. When I input -3, my output is 0. And when I input -6, my output is 2. So like a table that has kind of like a list of points, that's what this is as well. It's important to understand that both a table and a mapping in this context don't represent a continuous function. In other words, this represents a discrete function, which means that this is an individual point, an individual point, an individual point, and same thing with here. So you wouldn't connect the dots, so to speak. And so we're not including all the values that are in between those points. The only time we do that is if we have kind of a graph or an equation. So this is not really a common function, like not one that we would know off the top of our head. Kind of looks like it's, I don't know, there's linear, there's maybe some absolute value in here. So this is just a function that doesn't necessarily have a specific name like quadratic, exponential, logarithmic, whatever. What we're looking at here is, again, a table, or is a graph. This is what we we call this non-discrete. In other words, this is a continuous function, it's infinite, because all these points, we can find individual points off this graph, like when x is 2, what is y? When x is 4, what is y? When x is 2 point whatever, we could figure out what y is, or at least we could estimate it. However, because we connected all the dots, this is an infinite number of points that are on here. And so we're including all of the values in between. So it would be impossible for us to represent all of the points on this graph in a mapping or a table because there are infinite number of points. Likewise with a function, this is obviously probably the most common way. This is a square root function. Again, represents kind of a continuous function. You remember what a square root function looks like with a like kind of that hook shaped graph, which we'll talk about mostly in the next unit, but we'll talk about it in this unit or in the next lesson, but also in this lesson as well. Again, you can plug in any value you want for x and get an output. Now obviously if you know anything about a square root function, you will understand that there are some limitations. Like for example, if I plugged in -10 for x, I would get -10 plus 6, which is the square root of -4. I can't take the square root of -4 without going into imaginaries, which means that the domain is restricted, like there are some values of x that don't work, but for the most part, I can kind of plug in values and get an output. Now again, like I said, there are going to be some values that don't work. However, we can still find a whole bunch of different points that are on that graph. Sorry. All right, so what we're going to take a look at is kind of how to read the function notation. And I don't have my usual document camera, so I apologize for the video here, but I'm doing the best I can. All right, so anyway, here we go. So what we're looking at here is each of these things represent a different function. This is the f of x function, g of x, h of x, k of x. So this is referring to these 4 different representations on the side. So what I'm trying to get you to understand is just the notation. When I say f of 2, the 2, it's like basically saying f of x. Well, what am I replacing x with? I'm replacing x with 2. So this is my input, 2 is my input. What I'm asking you to do here when I say, perform the operation, I'm asking you to evaluate what f of 2 is. So you would go to your f of x function, which is this table. When my input, or my x value is 2, my output is -6. So that's what that value equals. Likewise, for the g of 3, this is my g of x equation, right, or function I should say. When I input 3, so these are my inputs, my output is -1. So those are being multiplied together, minus h of 1, that's our table, or I'm sorry, I'm saying table, it's a graph. So that means our input, so these are our x's, those are gonna be your inputs, right, as your y's are gonna represent your outputs. So when my input is 1, what is my output? Well, if I reach up to my graph, it looks like my output is 3. So I would go back here and I would say this h of 1 evaluates to 3, and then k of 3, I'm gonna go ahead and plug in. This one is, we can actually do algebraically, we can just plug 3 in. So I'm literally just plugging 3 in for x. This becomes the square root of 9, which is 3, and 3 minus 5, of course, is -2. What I want to remind you here is just to follow order of operations for this one. So notice that it's f of 2 times g of 3 minus h of 1 times k of 3. So you'd have to do all the multiplication first, which is why I put those in parentheses. So this would be 6 minus -6, and then 6 minus -6 is 12, right? Because you change that to a plus and a plus and, move on from there. All right, let's try a couple others. So the next one is h of 8 raised to the f of 2. So let's first use the h of 8. So h of 8 implies when I input 8, what is my output? So if I look at my graph, when I input 8, it looks like my output is 2. So h of 8 is going to represent 2. I'll change colors here. And then f of 2, again, when my input is 2, my output is -6. Over f of 9. So f of 9 means on the f of x equation, my input is 9, my output would be -1. So now let's remember a little bit about exponent properties. When I have 2 to the -6, we remember that we can rewrite that as a positive exponent by taking the reciprocal, or in other words, just kind of bumping it to the bottom. So that becomes 1 over -1 times 2 to the 6th. And 2 to the 6th is, so 2 times 2 is 4. So that's like saying 2 times 2, 2 times 2, 2 times 2. So that's 64. So this becomes -64 on the bottom. And whether you write the negative here or whether you write it up here, it doesn't really matter. But anyway, my answer is -1 over 64. All right, next thing we can do with functions is compositions. So you probably have done, hopefully, maybe some compositions in the past. What this means is we're gonna kind of like we're doing substitution property, if you remember from Algebra 1 or even a little bit from Algebra 2 when we solve systems. So what this means is kind of start from the inside out. So g of -3. So what this implies is that I'm saying, look at the g of x equation. When the input is -3, what do I get? Well, my output is 0. So I'm going to replace g of -3 with that answer, which is 0. And so now I'm saying, all right, well, now let's evaluate f of 0. So let's go up to the f of x equation. When the input is 0, my output is 4. So again, it's just kind of a composition. It's kind of like you're gonna use an answer from here to find an answer for here. So it's like I said, kind of like the substitution property. So h of k of 10. So start from the inside out again. So k of 10, let's go back down to our equation. So k of 10 means we're plugging 10 into our equation for x. So I would get root 16 minus 5, which root 16 is 4. 4 minus 5 is -1. So I'm going to replace this with h of -1. So I just replaced the k of 10 with -1. So now I'm going to go up here and say, okay, when my input is -1, so -1 looks about right here. What is my output? It looks like it's at 5. If you look at your papers, if you can see it, it looks like it's at 5. So my answer is 5. That jingling in the background is my dog playing with his toy, so I apologize. All right, letter C. Let's go ahead and do this one. Again, work from the inside out. So I'm gonna look at that f of 2, the first thing I'm gonna do. So when my input is 2, my output is -6. So I got k and then g of -6 plus 17 plus 1. So just watch all the parentheses and the order of operations here. So I just replaced the f of 2 with -6 because that was what I found out from my table above. So now the next thing I would do is do the g of -6. So the g of x equation is up here. That says when my input is -6, my output is 2. So now I'm going to replace this with 2 plus 17 plus 1. So again, notice I just replaced the g of -6 with the 2 because I got that from my mapping. And so obviously 2 plus 17 is 19. So we're going to evaluate k of 19. So we're going to go to our function here. K of 19 looks like 19, the square root of 19 plus 6 minus 5. Looks like I've got 5 minus 5, which is 0. So this becomes, this becomes 0, and then plus 1 gives me 1. So that's just a couple examples of how we can do compositions. And so when you do this on your own here, when we do the practice, I want you to try that again, just kind of work from the inside out. My favorite is the solving, which basically just means we're switching gears now. Instead of doing inputs, we're talking about outputs. So we're saying, what is the input that gives me an output of 9? So in an equation, that's just saying, let's solve for x. So we're gonna plug 9 in for k of x. We're saying k of x equals 9. The square root of x plus 6 minus 5. So do you remember how to solve a square root function? So if not, what I want you to remember to do is isolate this radical, so add 5 to both sides. I'm going to square both sides. That's how I'm going to get rid of that square root. And 14 squared is 196. And then I'm going to subtract 6. So what this implies, when my input is 190, my output is 9. So that's an ordered pair. You can think of it as the point 190 comma 9. If you were to graph this function, this point would be on this graph. Input, output. F of x equals -6. So let's go up to our f of x. So this time I'm saying the output is -6. So this is this one. The output is -6. What's my input? Well, that was fairly easy. It's just 2. H of x equals 3. So we're looking at here, again, our outputs. Our outputs would be our y values. So we're saying our output, So our output is 3. So when our output is 3, our input was, looks like 1 was our corresponding x value. So when y was 3, we kind of draw over till it hits the graph, and then look down and see what's the corresponding x value, and that looks like it's 1. We did a little composition here. So f of g of x equals 4. So what I want to do on this one is I want to do the g of x first. And so I'm going to say, I'm going to look at g of x, and I'm going to say, well, actually, I'm going to look at f of 4. Actually, I lied. I'm going to go back to f of 4. So I know that my output of whatever I'm doing here, my output has to equal 4. So if I go back up to this equation where my output is 4, my input had to be 0. So in order for whatever I had the input here, so like pretend like this is like represents the input of your f of x equation, right? So in order for me to get an output of 4, this g of x equation, or this g of x thing had to equal 0. Because in order for this to work, I had to have f of 0 equals 4. So let's go back up here, because f of 0 equals 4. When my input is 0, my output is 4. So now we realize that this g of x equation has to equal 0. So we're not quite done. So now we're going to go to our g of x equation and say, well, if my g of x output has to be 0, what are my inputs? Well, notice that there's 2 arrows coming from it, which means that there are 2 possible answers here. So my input could have been 0, or my input could have been -3. So my answer here would be x has to be 0 or -3. So again, the strategy here was to kind of look at it from like f of, and then think of this as just one value, like f of x equals 4. And so in order for us to figure that out, we figured out that in order for us to get an output of 4, we have to have an input of 0, which meant g of x had to equal 0. In order for that to be true, x has to be 0 and -3. You can cross off letter E. We're not going to do that one. All right, let's do some more. This is about compositions. So again, just kind of still using our concept about compositions. We're just going to use the function f of x equals x squared, and we're going to write a composition and then talk about what the name of it is. So this is what it would look like. So we're going to say a of x equals, so what you're doing is, in this equation, this is the one we're kind of referring back to. In that equation, we're replacing x with whatever we have here. So in this equation, I'm replacing x with square root of x. So instead of saying x squared, I'm going to say the square root of x squared. So again, it's like kind of like saying f of x, right? Or f of 3. You're replacing x with 3 in your equation. Well, in this case, instead of saying f of 3, I'm saying f of root x. So I'm replacing x with root x. I'm replacing x with the square root of x into this function. So again, kind of like the substitution property. So let's evaluate that. Well, the square root of x squared is just x. What type of function is that? Well, it's linear. So if I were to graph this, it would just be a straight line. Next one, b of x equals 5 times f of x squared. So what I'm looking for is, let me kind of switch over to this one. So what I'm looking for here is, again, kind of the same concept. I want you to look at what you're plugging in, like in this case, what is f of x? You're plugging in x into our equation. Well, f of x is already x squared, so we can replace f of x with x squared. We already know what f of x is. We set that up in the beginning, right? So I just replaced f of x with x squared. So let's do some math here. X squared squared is x to the 4th. So this function, if you remember from our polynomials unit, is called a quartic. On this one, you're replacing, in your f of x equation, you're replacing x with x plus 2. So if we go up here, instead of saying x squared, we're going to say -5 times x plus 2 squared, because it's just whatever this is, squared, because that's what our function says, and then minus 10. What I want you to do here is I want you to use the distributive property, and I want you to expand this out. So be careful, people make mistakes here. Remember that you're not just applying that power. This is the binomial times a binomial, which means you have to distribute or FOIL. So I'm going to leave the -5 out front for the time being. I'm going to distribute this out. And then I'm going to multiply through by -5. And then I'm going to simplify. So I'm just going to combine some like terms. So I get -5x squared, looks like minus 20x minus 30. All right, so we take a look at that function. That should be pretty obvious what type of function that is. It's x squared is the highest power, so that would be the quadratic. And then x times f of x. So remember, our original function is f of x, and f of x is x squared. So I can just replace f of x with x squared. Let's do some simplifying. X times x squared is x cubed. X cubed minus 10, that's about as simplified as you're going to get. What type of function is that? That is a 3rd degree polynomial, better known as a cubic. On this one, we're replacing x with x plus h. So so remember, our original function is this, right? So we're replacing x with x plus h. So this becomes f of x plus h becomes x plus h squared minus f of x. Well, f of x is already equal to x squared over h. So kind of take a look at what I did there. So again, all I did is replace x plus h into this function. So replaced the x with x plus h, and then replaced f of x with what the function was, which was x squared. Let's distribute. So remember, we're doing the distributive property here. We can't just apply that power. We must FOIL. So I get x squared. And if I distribute this out, this becomes xh, and this becomes xh, which is 2xh, plus h squared minus x squared all over h. If I simplify, my x squareds are going to cancel. I get 2xh plus h squared over h. I could factor out an h on top if I really wanted to. So I get 2x plus h over h. So I just factored on h from here, and then those h's cancel. So I'm left with 2x plus h. All right, one might ask, what type of function is that? Well, 2x plus h is a linear function. It's in terms of x. So again, the h is really just kind of an extra number here. We're just kind of using an extra variable. So this is still a linear function because 2x plus h is a linear equation. All right, last thing we're going to talk about today is called even and odd functions. And so an even and odd functions talks about symmetry. So what we're going to do is we're going to prove even and odd functions. So first, a function is considered even if it's reflective about the line x equals 0. Well, the line x equals 0 is better known as the y-axis. So if your function is reflective about the line x equals 0, then it's considered an even function. So again, parabolas are pretty common, right? Maybe an absolute value would be pretty common. It's an odd function if there's a 180-degree rotational symmetry about the origin. So the origin's right here, that's 0, 0. So notice if I took this and rotated it 180 degrees, it's gonna map onto itself. So this is called a 180-degree rotation. So think back to your geometry days when we did transformations, right? That's a 180-degree rotation, kind of counterclockwise, if you will, or clockwise, doesn't really matter. But anyway, you're taking this piece and you're rotating around. So if that's true, then this is an odd function. So we have a way for us to be able to prove this without having to actually look at the symmetry, like to actually show whether or not it's reflective over that vertical line x equals 0, or whether or not we don't have to show that it's like 180-degree rotational symmetry. There's an algebraic way behind it. So the algebraic way says if we go f of x equals f of negative x for all values of x. Okay, so what this means is, kind of like in normal terms or in normal speak, if I plug in, I'm just gonna write it down. If I plug in negative x for x, I get, in other words, my output, my original function. So if I plug in negative x for x, I get my original function. It's odd if I plug in, so I'm going to write it in words, if I plug in negative x for x and get -1 times my original function. So it sounds a little harder than what it actually is. So all we're really going to do here is we're going to plug in negative x for x, okay? And we're going to see if we get the same thing back out, like if we end with where we started, or if we get like -1 times whatever we started with. And if we don't get either, then we say it's either even, odd, or my favorite, neither. So let's do this. So this first example, f of x equals x squared plus 1 over x. So I'm going to plug in negative x for x. So wherever I see x, I'm going to plug in negative x. So I get negative x squared plus 1 over negative x. So again, every place you see x, you're substituting in negative x. Well, then let's simplify. Negative x squared is just x squared, because a negative squared is always positive, and this is negative x, right? So is this my original function? Clearly not. There's definitely a negative sign here. Is this -1 times my original function? It is, right? If I factor out a -1, like just put the -1 out in front, right? It's -1 times my original function. Because here's my original function, and it's -1 times that. So what do we consider this to be? Odd. Okay, let's do another one. This time, again, I'm going to plug in -x wherever I see x. So -x to the 4th minus -x squared plus 3. -x to an even power will be even. So this is x to the 4th minus -x squared is just x squared plus 3. So notice that my output is the exact same thing as my input. My output is exactly the same thing as my original function, x to the 4th minus x squared plus 3. When that occurs, we know this is an even function. Can you take a guess at what the last answer is going to be? All right, let's plug in -x. So if I plug in -x, I get -x to the 6th plus -x cubed. So a -x to the 6th would be x to the 6th, right? And then a -x cubed would be a -x cubed, because a negative times a negative times a negative is a negative. So is this -1 times my original? Well, let's factor out a -1. That's how I kind of always check. If I factor out a -1, I would get -x to the 6th plus x cubed. Notice that's not the same thing. That is not -1. In order for this to be odd, this has to be -1 times my original function. Well, here's -1. Is this my original function? Close, but not quite. There's that extra negative sign. So this doesn't follow either format. It doesn't get me back to my original, doesn't follow the -1 times the original. Therefore, it is considered neither. All right, so I apologize for the video. I don't have my document camera, so I'm having to hold my iPad and actually do this at the same time. So I apologize, it's a little shaky. What we're gonna do now is you guys are gonna hopefully kind of digest this a little bit, come to class with some questions, and then you're gonna work on some practice. I can see if you understand it. And if you don't, that's where I come into play. All right, have a good rest of your night. Bye.